Okay, so we introduced the concept of a random function that can be seen as either a large number of realizations of functions that all have the same statistical properties, together called the ensemble, or it can be seen as a collection of mutually dependent random variables, and they can be, and that is all described by the so-called multivariate probability density function. Now, a very useful property of a random function is called stationarity. And loosely speaking, a stationary random function means that the statistical properties are the same everywhere. So the mean is the same everywhere, the variance, the skewness, all the probability density functions, the bivariate, the multivariate probability density functions, they are all the same everywhere. And that is more loosely defined. We will define it more strictly later on. And this is an example of a realization of a stationary random function, for instance. And this one is obviously not stationary because you can see that the mean is increasing. Yeah, so there's a trend. So that's a non-stationary random function. In this case, it is non-stationary because there is a certain periodicity in it. Yeah. Now that is actually what you will see in most of the hydrological time series that we have. There's always some stationary or some periodicity in it, obviously, because at least in most parts, except for the tropics, the precipitation and evaporation, they change drastically throughout the year. So also the difference between precipitation and evaporation, and therefore discharge. So but you have a yearly cycle by definition. By subtracting that, basically correcting this periodicity often turns a periodic non-stationary random function into a stationary random function. Now this is a realization of a random function that is also non-stationary, because you can see that the variance is slowly decreasing in time. Yeah, this is called heteroscedastic, so-called heteroscedastic random function, which means that the variance changes over space or time. And then there's one here that where you can see is that the correlation structure. So the dependency between variables at two different times, that it also changes over time. You can see it becomes much more smooth over time. So the correlation between any two variables that are, say, maybe 10 time steps apart increases with time, as you can see. Yeah. So these are all examples of non-stationary random functions. Now going back to so stationary random function, loosely speaking, has the same properties everywhere. Now you can play around a little bit. The most time series obviously is also non-stationary because of its periodicity in peaks, as you can see. You can play around with this you can find it on Blackboard. Play around a little bit with. This is an example. You can actually, it's a very, these are based on JavaScript, where you can zoom in and zoom out on the time series. Just try it and play around with it. This is an example of a realization of a stationary space random function of space or random field. Yeah. And this is an example of a non-stationary random field where there's a trend visible, as you can see. Now, why is stationarity such a useful property of a random function? Why do we assume it so often? Well, for that, we need to go back to our multivariate random or a multivariate probability density function that describes the that describes in full the statistical structure of a random function. Yeah. So remember that we ended the previous part by saying that everything there is to know about a random function is encoded in the multivariate probability density function. And if we know the joint probability density of any set of points at any set of locations or time steps, we can calculate that one. We have everything there is to need to know about the random function. Now, if we take the simplest form of the multivariate Gaussian probability distribution, this is the of a multivariate probability distribution. This is the Gaussian form of it, and as you can see here, this is what it looks like for n different locations in time or space. Yeah, so we already saw this from our previous lecture about random variables, that if you have n is, suppose n is 10, yeah, so this may for instance be discharge at 10 points in time, or hydraulic conductivity at 10 locations, then even for 10 points you need 65 parameters to fully characterize the full probability, multivariate probability density function. And you need 10 values of the mean, 10 values of the variance, and you need 10 times 9 divided by 2 cross-correlation coefficients. So even for the most simple form of multivariate probability density functions, to fully characterize a random function, we need a hell of a lot of parameters. So this is actually not feasible. So what we do is to make it possible to statistically characterize random functions, we add assumptions. And most of the important assumptions that we can add is so-called stationarity. Now let's see how this works. Now we start by saying that there are different forms of stationarity, and the most strict form, or the most extensive form of stationarity, is called strict stationarity. And a random function is said to be strictly stationary if the multivariate probability density function is invariant under translation. So what does it mean? We take any set of points, and if we move them around, but by not changing the distance between those points, we get the same joint probability density. Yeah. So if we calculate the probability of Z1, probability density of Z1 to Z5 at locations T1 to T5, yeah, and we calculate and we do the same at different locations where we move the whole configuration, say a time interval T prime to the right, then the probability density for this the same Z1, Z2, Z3, Z4, Z5 is exactly the same. So it doesn't change. And this means for all configurations that you can think of, for all different TI, and for any distance you change or you move this configuration across the time axis. Yeah? This this means for all. So this is in time, or we can do a similar thing in space. We take any set of points, yeah, as long as we don't change the configuration and we move it about, then we get the same probability density. Now remember that now moving translation has is a vector, right? So it has a vector with two components, a translation in the x direction and a translation in the y direction, and it also have a length of the translation, which is so-called the norm of the vector, or the length of the vector, which can be calculated by the rule of Pythagoras. Yeah? So changing this configuration, moving it about, gives you the same probability density for any set of points and for any configuration. As long as you don't change the mutual distance between those points, you get the same probability density. By the way, this is not the same as rotation, because if we rotate, yeah, that's a different type of operation. So if the probability density remains invariant, remains the same under both rotation, but also under, translation, but also under rotation, like here, we rotate it like this, then it's called isotropic. And we come back to isotropy in the next Thursday's lecture, in random function part 2. So now we're only talking about this translation. So this is a so-called strict stationary random function. Now we can relax this a little bit, and if we don't demand that for any set of points this is valid, we can say, well, suppose that we say, okay, we have a random function that it's only valid for 2 points. So we take 2 points, T1 and T2, and we say, okay, the bivariate probability density of any value Z1 and Z2 that may occur at these 2 points doesn't change as long as we move it across the timeline, or in space, it's across the space domain, obviously, as long as the distance, and in space also the direction between the 2 points remains the same. So we're taking 2 points and we're moving them about. The bivariate probability density function doesn't change. That is called the second order stationary random function. So that's a little bit less strict than a strict stationarity. Yeah, something can be second order stationary, but not so the bivariate probability density invariant under translation, but it doesn't mean that it's also strict stationarity. The other way around, that's of course the case, because if something is strict stationary, it also means it's valid for 2 points, because this is for any set of points, so also for 2. So if something is strict stationary, it is second order stationary, but if it's second order stationary, it's not necessarily strict stationary. Then we go to an even more relaxed, less strict definition of stationarity, and that's called wide sense stationarity. For a wide sense stationary random function, we say the mean is constant, the variance is constant, and finite. That seems to be a little bit an enigma. Why would he say? Why can't it be infinite? Well, we come back to that later on in chapter 7 on geostatistics. There's a certain form of there's an even more relaxed form of stationarity that can work with infinite variances, but we'll talk about that later. Right now, wide sense stationary random function means that it has a constant mean, so the mean is the same everywhere. The variance is the same everywhere across the timeline or in space, and the covariance between any set of points only is a function of its distance. So if you take the covariance between T2 and T1, yeah, whether it's here or whether we move the whole configuration T prime to the right, it only depends on the distance between the two. Yeah? So you can see that the covariance between any set of points T1 and T2 only depends on the distance between T2 and T1. So you can actually replace T2 minus T1 by a single variable, which is called the lag. Yeah, LAG, the lag. So therefore, you can plot the covariance as a function of lag. Yeah, and what you typically see with a wide sense stationary random function is that this covariance decreases when the distance between the 2 points also increases. Yeah, and of course, if the distance is 0, then the covariance is exactly equal to the variance. And it's also a symmetrical function, as you can see. Yeah? So the covariance between T2 and T1 or T1 and T2 is the same. Yeah, it doesn't matter which one comes first. This is often called an even function. Now there's also a certain length at which the correlation becomes zero, or that's called the decorrelation or correlation length. Yeah. So, and instead of the covariance, we can also normalize the covariance by the variance of the random function, which is constant in case of a wide-sense stationary random function. And then we have a correlation function, yeah, which is 1 for the correlation lag 0, and for a large lag going to infinity, or a lag lag that is larger than the correlation length, it becomes 0. Now, the correlation function, of course, has a big impact on how the realizations of the random functions, how they look like. And so we play around with random function and correlation. Let's run the thing. So, as you can see, this is a realization of a random function. We can resample, of course, but it's all realizations of the same random function. Now, what is interesting is to look at the dependency. This is not a this is not the this is a measure of dependency. Yeah. So here you can see the correlation function. So if we screw up the dependency in time, you can see that the random function becomes much more smooth. You see it has, of course, so this is the, and this is the correlation function. Yeah. If the correlation is very small, we get something that is very close to white noise. So it is not dependent in time in this case. Yeah. Now, of course, you can also change the variance, but that will only change the y-axis here. So this is a very important property of a random function, a wide-sense stationary random function. That's the correlation function or the covariance function. Yeah. Now let us now go back to our multivariate probability density function. Yeah. And make the following assumption. We assume that our random function is wide-sense stationary. Wide-sense stationary, yeah. So the mean is the same everywhere. Well, so you can see we have the same mean. The variance is the same everywhere, so we see you have the same variance. And the covariance is only a function of the distance between two locations. Yeah. As you can see here, only the distance between the two is important, and not the actual values x1 and x2. Now, if we look at a function like this, a correlation function like this, it would typically look like this. For instance, I will just write it down. So a correlation function like this would typically we typically have look like this. Rho as a function of theta would be equal to e to the power of minus theta divided, theta is the lag divided by L. Yeah, and usually you take the absolute value of theta. So you see there's only one parameter, additional parameter that you need that describes that's this dependency parameter, yeah, that describes how fast it goes to 0, yeah. So this dependency parameter, that's this lambda here. Now, if we go then back to our wide-sense stationary random function, we can see we have the same mean, that's one parameter. We have the same variance. There's also one parameter. And we have one parameter that tells me how fast the correlation decreases as a function of the distance, the lag between 2 points. So only 3 parameters. So that's a totally different picture than the 65 that we had for 10 random variables before. And it's regardless of the value of n. Yeah. So this means that actually this means that any set of points, when we assume it that they come from a realization of a wide-sense stationary random function, and they're described by a multivariate Gaussian probability distribution. Yeah. That assumption that we add makes that we can describe the total random function with only a few parameters, regardless on how many points we take. This also means, by the way, because this now is the multivariate probability density function is now completely defined for any set of points. It's also strictly, and it's the same for any set of points. With it doesn't mean where these points are located. It's also strictly stationary. Yeah. So this is what we learn from the combination of wide-sense stationary random function and a multivariate Gaussian probability distribution is sort of a golden combination that is often used in many of the literature when they talk about random functions of space or space-time. That assumption is often used. It doesn't mean that reality is such, but it's a property of the mathematical model to make the random function to describe reality tractable, with a number of parameters that we can actually estimate. So if reality deviates too much from stationarity, what we often tend to do is make it stationary. For instance, if there's a trend, we detrend it. If it's heteroscedastic, we multiply it times a prefactor that corrects for heteroscedasticity, for instance. And that's the same for the Gaussianity. If the thing is not Gaussian, often some transformation is applied to make sure that the variables are Gaussian. So typically, for instance, in 2 dimensions, if 2-dimensional random fields describing conductivity, we know that the log normal distribution is very well suited to describing conductivity. So often the natural logarithm of conductivity or the base 10 logarithm of conductivity is used, and that is then described by and then after detrending, the remainder is described by a multivariate Gaussian probability distribution assuming wide-sense stationarity. So we only need the mean and the covariance function, and the covariance function is described by 2 parameters, the variance and the decorrelation length, the lambda. Okay. Just to give you, say something about the relationships between different forms of stationarity. Like I said, if something is strictly stationary, it's also, it means that the multivariate probability density function is invariant under translation. If it's second order stationary, the bivariate probability density function is invariant under translation. And of course, multivariate also means bivariate. If it's for n variables, also equal for 2 variables, then we can also say that if something is strictly stationary, it's also second order stationary. Wide-sense stationarity means that the mean and the variance are constant and the covariance is invariant under translation. Well, take it from me, if the bivariate probability density function for any set of points, for any location of 2 points, is invariant under translation, also its mean and covariance that are part of the description of the bivariate probability density function are also are constant and invariant under translation. So a second order stationary random function also implies that the function is also wide-sense stationary. But it cannot be the other way around. Something can be wide-sense stationary and not second-order stationary. For instance, if the thing is not Gaussian, yeah? Something can be second-order stationary, but not strict stationary. So this is the order of things. And then finally, there's this thing. If on top of that, if on top of a random function being second-order stationary or wide-sense stationary, and we know that the multivariate probability density function has a Gaussian form, then by construction, it's also strictly stationary, because in this case, we only need these three parameters to fully characterize the multivariate probability density function, which is the same everywhere. If the configuration of the points, the distance between the points and is known. Yeah. So this is the order of things.